The inverse of a function. Definition. Let f be a one-to-one function with domain A and range B. Then its inverse function has domain B and range A and is defined by f inverse of y equals x, which is equivalent to f of x equals y for any y in B. By definition, the inverse function undoes what f does. If we start with x, apply f, and then apply f inverse, we arrive back at x where we started. Similarly, f undoes what f inverse does. In general, any function that reverses the effect of f in this way must be the inverse of f. The definition says that if f takes x to y, then f inverse takes y back to x. If f were not one-to-one, then f inverse would not be defined uniquely. The arrow diagram in Figure 6 indicates that f inverse reverses the effect of f. From the definition, we have domain of f inverse equals range of f, and range of f inverse equals domain of f. Example, finding f inverse for specific values. If f of 1 equals 5 and f of 3 equals 7, find f inverse of 5 and f inverse of 7. Solution. From the definition of f inverse, we have f inverse of 5 equals 1 because f of 1 equals 5, and f inverse of 7 equals 3 because f of 3 equals 7. Figure 7 shows how f inverse reverses the effect of f in this case. Notice that in the function f, it has domain A and range B. 1 and 3 are in the domain, and 5 and 7 are in the range. And the function f maps 1 from the domain to 5 in the range, and it maps 3 in the domain to 7 in the range. F inverse has a domain of B and a range of A, and 5 and 7 are in the domain of B, 1 and 3 are in the range of A, and F inverse maps 5 to 1, and it maps 7 to 3. Warning! Don't mistake the negative 1 in F inverse for an exponent. F inverse of x does not mean 1 divided by f of x. The reciprocal function, 1 over f of x, is the same as f of x all raised to the negative 1. Notice that's different notation. One-step inverse functions, operations that undo each other, addition and subtraction, multiplication and division, powers and roots. Examples, if f of x equals x plus 1, then f inverse of x would equal x minus 1. That is, if we start with a number x and add 1, then to undo that, we start where we left off and subtract 1. So subtracting is the inverse of adding. Second example, if f of x equals 2 multiplied by x, then f inverse of x equals x divided by 2. That is, starting with a number and doubling it, and then to get back to the original number, we would divide it by 2. So dividing represents the inverse of multiplying. And third example, if f of x equals x cubed, then f inverse of x equals the cube root of x. If we start with a number and cube it, then to get back to that original number, we take the cube root. So the cube root function is the inverse function of the cubic function. And a fourth example. If f of x equals x squared with a domain of the set of all x such that x is greater than or equal to 0, and we need to restrict the domain so that x squared is a one-to-one function, then the inverse function of f equals square root of x. That is, if we start with a number and square it, then to get back to the original number, you take the square root. These properties indicate that f is the inverse function of f inverse. So we say that f and f inverse are inverses of each other. Now let's examine how we compute inverse functions. We first observe from the definition of f inverse that y equals f of x is equivalent to f inverse of y equals x. So if y equals f of x, and if we are able to solve this equation for x in terms of y, then we must have x equals f inverse of y. If we then interchange x and y, we have y equals f inverse of x, which is the desired equation. How to find the inverse of a one-to-one function? Step 1. Write y equals f of x. Step 2. Solve this equation for x in terms of y if possible. Step 3. Interchange x and y. The resulting equation is y equals f inverse of x. Example. Find the inverse of the function f of x equals 3x minus 2. To start out, we replace f of x with y, and we write y equals 3x minus 2. Then we want to solve the equation for x. The first step is to swap sides and to add 2 to both sides, and we get 3x equals y plus 2. Next step is to divide both sides of the equation by 3, and we get x equals y plus 2 all divided by 3. Then we interchange x and y, and we write y equals x plus 2 all divided by 3. And finally, we replace y with f inverse of x, and we can write the inverse function as f inverse of x equals x plus 2 all divided by 3. Graphing the inverse function. The principle of interchanging x and y to find the inverse function also gives us a method for obtaining the graph of f inverse from the graph of f. If f of a equals b, then f inverse of b equals a. Thus, the point a comma b is on the graph of f if and only if the point b comma a is on the graph of f inverse. But we get the point b comma a from the point a comma b by reflecting in the line y equals x. See figure 8. Therefore, as figure 9 illustrates, the following is true. The graph of f inverse is obtained by reflecting the graph of f in the line y equals x. And I'd like to illustrate for you another example. In the example, we started with the function f of x equals 3x minus 2 and determined that the inverse of f equals x plus 2 divided by 3. And I've taken both of these linear functions and graphed them here on the same coordinate plane. And the function in red, the line in red, is y equals 3x minus 2. The line in blue is y equals x plus 2 divided by 3. And I also graphed the dashed line is y equals x. And notice that the red and blue lines appear to be reflections in the line y equals x. Let's take a look at some points that are on these lines. First of all, looking at the red line, this point right here that I've indicated it has coordinates 2, 4. And its inverse function, y equals x plus 2 divided by 3, there's a point on this line that has coordinates 4, 2. Secondly, if we go back to the red line, y equals 3x minus 2, it has a y-intercept of 0, 2. And the line in blue, its inverse function, y equals x plus 2 over 3, has an x-intercept of -2, 0. Notice the coordinates of the points are interchanged. Thirdly, on the original function y equals 3x minus 2, we have a point on this line of -1, -5. And on the inverse function, one of the points here is -5, comma, -1. And finally, the red and blue lines intersect at the point 1, comma 1. And if you interchange those coordinates, then you are still at the point 1, 1. And so our functions intersect each other at this point. So here you can see 4 examples of points that are on our original function, our original red function, and then if you interchange the coordinates, you get points that are on the inverse function.